This is Color for Digital Design, Session 6, and we're talking about color relativity and also printing. My name is Alvalin Lundgren. So color relativity is a theory based on observation of color interactions, how colors work together, and why we see color the way we do. The theory was developed by Josef Albers, a colleague of Johannes Itten at the Bauhaus. And the idea of color relativity is simply that the color that we see is affected by the surrounding colors. And this happens every time we look at something. And we can use this to manipulate color for our purposes as designers and artists. For example, we'll look at this top row. The background colors, the larger squares, are all achromatics, going from black to a light gray. The orange is a shade, meaning it's not full saturation orange, but it is darkened with black. But here we see it darker on the lighter square. We see it lighter on the darker square, and we see it even lighter on the black square. With the blue-green, we're seeing this color lighter. It's darker over here on the lighter yellow. If you notice, there's a kind of a vibration, a visual fluttering along that edge. That's an indication that the value contrast between the blue-green and the orange is minimal. In other words, there's very little difference in lightness and darkness between these two colors. And so they're actually starting to fight each other. And that's why the center square seems a little bit unsettled. We look over here, it looks very stable and quiet. And over here it's very quiet, but here it's kind of jumpy. And we'll look at the yellow against the light blue and against the mid-value blue. So here it's looking darker. It's also looking more yellow. Here it's looking lighter and more yellow. And here it's looking lighter still. A color is more easily manipulated by surrounding colors, meaning that we can push it around and make it appear quite a bit different when the color is less saturated. So here we have a yellow that's been shaded. Against the blue-green, it's looking darker than this because it's on a lighter background. And it's also looking red because of the after image of the blue-green. So the blue-green is adding red-orange into the yellow. So this is looking very warm. This is looking very cool. The orange is adding blueness to the yellow. And the orange being darker is causing the yellow to look lighter. So where we talked about relative value a couple sessions ago, that is part of the color relativity or the interaction of color. Here we have two different blues, one very vibrant and a little bit darker, one a little more muted, a little warmer and lighter. And we have a tinted orange. And so the orange is directly complementary to both blues. So there is not that much difference between the two colors visually. Here on the red-orange, the orange is barely discernible. The values are pretty much the same, but it's looking quite yellow. Against the green, it's now looking quite red. And it's a lot lighter because the green is darker. So the idea is that looking at the hue circle, if you have one color here sitting on top of another color, here, the orange in this case would push the yellow away from it toward the blue side or the cool side of the hue circle. And that's exactly what's happening. On the other hand, the blue-green, which is here, is going to push the yellow, which is here, away from it around toward the red and cause the yellow to appear warmer and as if it has red in it. The after image or the complement of the blue-green is the red-orange. So the blue-green is trying to force the yellow to go as far as it can toward the complement of blue-green, trying to balance. So you can have a lot of fun manipulating color and trying and testing and see what happens with pushing colors around. But then you can also use this to your advantage as a designer for mood, for effect, for visual hierarchy, to balance a design, and for any other purpose that you might need when working with color. And here we're trying to take different colors. This is a yellow-green, and this is a yellow, and make them appear to be the same. And we do that, again, by what we surround it with. So this is looking now more yellow and lighter than this. This is looking more red and a little bit lighter than this. But these are looking fairly close. But if I pick this up, we see that that's the color that it matches. It doesn't match that, and it definitely doesn't match that. So we can take two different colors, and by what we surround those colors with, maneuver those two colors to appear very similar or even the same. Remember that seeing, to perceive anything, is to perceive in color. We see color. We see because of color. And color, of course, is a property of light. So the afterimage happens all the time. Color interaction happens all the time. Digital technology is very much involved in color printing. The only time it's not is with letterpress printing. And letterpress is what we see in this image, where we have movable type and everything is put together by hand and everything is controlled by hand. Letterpress printing has made a comeback in recent years, a lot in response to digital technology. Letterpress uses spot color rather than process color, and it's often used for very small print runs when you want high quality. So printing of any sort involves the subtractive color system because we're using pigments. So light is reflected off a surface. It does involve the additive system because, first of all, we have to have the additive before we can see the subtractive, but also the subtractive colors that are used filter the direct light of the additive system, giving us the colors that we see. The subtractive pigments are translucent, or they're totally opaque, letting no light through. Printing also involves some sort of surface or substrate which the inks adhere to. For color printing to work, for anything that is pigment-based, we need the additive system, we need direct light source, we need pigments of some sort, and we need surfaces. So those three things. The pigments, as I mentioned, act as filters for the light. The visual results of printing, just like the visual results of painting or drawing, are subject to the quality of the light. They're also subject to the surface quality, meaning the quality of the paper, the texture, and the quality of the pigments that are doing the filtering. There's digital printing and there is traditional non-digital printing. And non-digital would be spot color, four-color process, letterpress, as already mentioned, screen printing, lithography, etching, and block printing. Each one of these can be done without digital technology and always used to be. Nowadays, spot color printing, four-color process, screen printing all involve some aspect of digital technology along the way. When we think of digital printing, generally we're going to think of lasers and inkjets, stochastic printing, dye sub, and xerography. Xerography, of course, is photocopies. That's a form of printing. Spot color printing, you can print one to as many colors as you can afford to print. The color is pre-mixed. The color is chosen, specified, and notated by an ID number or a specific name. So as we're looking at this can, we have an ID number and we have the name. It's Pantone Yellow. You might be familiar with Pantone colors and Pantone charts and Fandex. So essentially, you choose colors almost like a color picker and coordinate them together and specify that to the printer. They mix the inks according to the formulas for the colors that you've requested, lay them in the ink troughs, and get the printer going. With spot color, you're pretty much assured of the final result. If you specify Pantone red, that's what's going to be printed. That's what you're going to see. The variable with spot color printing is going to be the substrate. How bright the substrate is, the texture of the paper, the luminance level, and the absorbency factor. Paper that's more absorbent will dull the color because the color sinks into the paper. A coated paper or a very smooth uncoated paper will cause the ink to sit on top of the paper with very little absorption. Process color, four-color process printing, utilizes the subtractive primaries, cyan, yellow, and magenta, and it adds black. Cyan, magenta, and yellow filter their additive complement, red, green, and blue. So in process printing, those pigments act as filters for the direct light. Black is added for depth and value contrast, for clarity. And process color printing also uses a visual phenomenon known as optical fusion or optical mixing. With optical fusion, you're not mixing color and then laying it down on the paper. Instead, you lay down colors in very small amounts, and then you add distance so that the small amount of color and the increased distance will optically fuse the color into a new color. This is the basis of pointillism and impressionism, and you can think of it as pattern. The ink goes down on the surface in a pattern, a dot screen. So an example of optical fusion is this impressionist painting by Petitjean. The enlargement, we see the dots very clearly. As it's reduced, it fuses together and becomes more solid. And as it gets very small, we lose the sense of the dots and it gets quite solid. Comparing admixing, which would be for spot color, or when painting, you're mixing a color and then applying it to the canvas. If you take yellow and magenta, you will achieve orange. If you blend green and magenta, you will achieve a gray. So this would be mixed together to get this. This is what would be applied to the substrate. This and this would be mixed to get that. That's applied to the substrate. But with optical mix, you can take the two colors and lay them out in a pattern or a dot screen or a line screen, and the smaller the dots, meaning the more dots you have per inch, and the more dots you have per inch, the more the colors will fuse into a new color visually. So here we have red and blue together in a traditional subtractive sense, and we have a checkerboard. The more squares in the checkerboard, the smaller the squares become, and the smaller they become, the more they fuse. So now we have a violet based off the red and the blue. This is the concept of process printing. Each color, yellow, cyan, and magenta, goes down onto the paper one at a time in layers. Each is laid out in a dot screen. It's not solid color. And where things juxtapose and overlap, we get new colors. So here we have the green, orange, and violet, and where everything comes together, we have black. And you can see it's not a true black, it's really a dark gray, and so that's why we actually add black and have a 4-color process rather than a 3-color process. So understanding process color, if we have red, green, and blue coming from the additive light source, the white light, and red is being absorbed by the pigment, but blue and green are being reflected off the pigment will appear to be cyan. If we have red and blue reflected, but green being absorbed, the pigment will appear to be magenta. If blue is being absorbed and red and green reflect back, we see yellow. Where the pigments overlap, here in the case of magenta and the yellow, the magenta will absorb the green, the yellow will absorb the blue. The only thing that comes back to our eye is the red. So we will be seeing this as the fusion of the magenta and the yellow. If we have a lot more yellow, it's going to appear more orange. The overlapping of cyan and yellow, the cyan will absorb red, the yellow will absorb the blue, leaving only the green part of the spectrum to kick back to our eyes. And here, the red is absorbed by the cyan, the green is absorbed by the magenta, and the blue is kicking back. So what we are seeing here will be blue. The key is that the pigments are transparent. So light goes through the pigments to the surface of the paper. The surface of the paper is a reflective light source. It reflects the light back through the pigment to our eyes. The pigments filter the light. The paper acts as a secondary reflective light source. And as you can see, the pigments filter their additive complements. So magenta, being the opposite of green, will filter green. Yellow, being the opposite of blue in the additive, will filter out blue or remove it. And cyan will filter out the red part of the white light spectrum. It's in process printing that additive and subtractive really do come together, and having high quality result with process printing means you have to have good pigments, good substrate, and a decent light quality. Now if you're printing on newsprint, it's highly absorbent and you're not going to have good color results. You will lose clarity in the image, things will get really fuzzy, the ink definitely absorbs pretty much into the paper. When you're printing on newsprint, you want to add a little more contrast in your digital file. When you're printing on uncoated paper, it's a little less absorbent than newsprint, but the ink is going to sink into the surface of the paper still. You're going to have better color clarity on uncoated paper, whether it's book weight, writing weight, or it's cover stock, than you would with newsprint. But you're not going to get the same clarity of color as if you have a coated paper. And coated papers come in a matte and a gloss and a luster, and those are three different kinds of paper surfaces, and the same color will appear differently on each one because of the reflective quality of the paper surface. So when you're sending things to print and specify the colors to use and the paper stock to be used, you have a lot to think about. Issues with paper are its opacity. Thin paper will allow color to be seen from the opposite side, and we see that a lot in like news magazines and catalogs and things like that. A thicker paper is less translucent and allows less light to pass through, so a thicker paper doesn't allow us to see the image on the back side of the sheet as easily. The luminance level of the paper also is an issue. A brighter luminance, in other words, it reflects more light back, will create a better, more accurate color result. Something that is less luminant is going to be more yellow. Remember white point, the higher the white point is set, the bluer, the lower the white point, the less light you have, it will appear warmer. Same thing is true with paper. If the paper is like a natural white rather than a bright white or a solar white, it's going to have a little warmth to it. And if you're working with a colored paper, then that's going to affect how the ink appears. The texture of the paper. If the paper's rough, color will appear duller because light is reflected off the paper in a scattered manner. It's going all over the place. A smoother paper reflects light back in more regular patterns. The reflected wavelengths are all going in uniform directions. And so color appears brighter on a smooth paper and duller on an uncoated paper. That's why when you work with Pantone color and you're specifying print color with the Fandex, you're looking at the coated, the matte coated, or the uncoated, and the same ink color will appear differently on those different surfaces. So here's what happens with color printing. You have a digital file. It goes through a color separation process. The digital process separates the full color image into 4 cyan, magenta, yellow, and black. And a plate is made for each one of those 4 colors. And then in the printing process, the color is laid down. And it usually starts with cyan, then you add the magenta, then you add the yellow, and you can see here we have a full color image, but there's no depth to it. It's very kind of washed out. And then when we add black, we get more detail, more depth, and a greater range of color. When you're dealing with process printing, especially high-end printing, and you're working with an on-ground printer, you will probably be involved in press checks in one way, shape, or form. And a press check is there just to make sure everything is printing what's called on register, and that the color is working properly. And with press checks, you're right there at the start of the print run, and the pressman will pull sheets from various points in the run for you to look at. And you will look at them under a color-corrected lighting situation. And what you want to look for are shifts in neutral colors or chromatic neutrals. So in the case of if this magazine spread were being printed, you would want to look at the skin tones, and you would want to look at anything that's supposed to be a neutral gray, like the background. You don't want to look at more chromatic colors. It's easier to see color shifts looking at neutralized colors or true neutrals. For every job that you send off to a printer, they will provide a contract proof from your file, and before any plating is done, you will approve the contract proof. And that will be your standard for the quality of color that comes off the printing press. Here is a true neutral. It has no chroma whatsoever, so it's a true gray. You can see in comparison, there's some blueness here, there's redness here, and there's yellowness here. So it's in these color shifts within the neutrals that you want to verify that color is working the way it should. You're going to use your contract proof as the color standard. Now, a press check cannot be done with a digital proof. You cannot do it online because you're not looking at the ink colors. You're not looking at the final output. You are looking at a digital simulation of the hoped for result. So if you work with online printers and you want a physical proof, it's going to cost a lot more money, which kind of defeats the purpose of working with online printers. Press checks generally you don't have to do when you're dealing with a spot color run, especially if it's a 1, 2, or 3 color, because again the inks are not fusing optically and you don't have to worry that much about things being off register. If you do a press check for spot color print runs, registration is what you're going to be looking for mostly, not color accuracy. So all of this is in regard to offset for color process, offset lithography, where you provide a digital file and the printer takes it and runs it through pre-press, gets it plated, gets it on press, and it goes through those really large digital presses that take up the whole room, like this one. Each of these is an inkwell, and you feed the paper from one end, so you see the paper stacked up here, ready to be fed. This is a sheet fed. This is sheet and not rolls of paper. And so each one of these will be snagged and pass through the blankets and the rollers and come out and stack on the other end. And so cyan, magenta, yellow, black. So now I just wanted to do a quick rundown of digital print technology. Not go into much detail, but so that you'll have an understanding of the differences. Digital printers will divide a page into a grid, laying down color grid by grid. So they lay down patterns of ink to create an overall image. You've probably heard the word dithering, but dithering is how those patterns are created. It's the process that the printer uses to create the screen patterns. The print heads contain nozzles. The more nozzles that a print head contains, the finer the dots. So a digital printer that can run a G-Clay print, which is a very high-end, very detailed image, is going to have a lot more ink nozzles. A lot more ink is going to go down on the paper. You're going to get a richer, more robust image. So a piezoelectric type of inkjet will actually move ink through the nozzle onto the paper by vibrating the nozzle, kind of like shaking it. And Epson technology and some Canon printers do this. Bubble jet is where the ink gets heated, and in that way it spews out of the nozzles. And Canon has some printers that operate this way, and HP printers operate this way. Now, the reason why it's good to know this is because not all inkjet printers use all inkjet paper well. You have to be careful about the kind of paper you get for your particular print and its technology. There are papers that are made like by Boise Cascade or Neenah paper that say they're suitable for all inkjet possibilities, but in reality you still have to test to be sure. I've run some paper and that said it was multi-use inkjet, and it worked well in one printer, and the other printer it just was terrible. So you have to choose your paper wisely when you're dealing with inkjet printing. You might be familiar with dye sublimation printing. It's when you get like a full halftone image that's printed. It's usually on a banner or on t-shirts or trade show displays. So you get a full continuous tone image, and it's actually an oil-based dye applied to a synthetic substrate. Dye sublimation does not work with standard traditional fabrics, so you can't print onto cotton. It has to be a totally synthetic fabric or substrate. In dye sub, the dyes are heated from a liquid state immediately to a gas state. It creates a thermal transfer process. Laser printers use a toner technology similar to photocopying. So there's a dry toner, and static electricity is used to fuse the toner to the paper. Digital to plate is similar to four-color process offset. You can actually go through an offset process with stochastic printing. But traditional offset is going to use a regular dot screen pattern that looks like this. And there's only so fine or so small that those dots can get. With stochastic printing, the dots are laid down in much more random patterns, and so you can get much finer detail. And so a digital to plate technology allows for richer color, greater detail in an image, sometimes too detailed. If the image isn't edited properly, you'll see all the flaws in a person's face. Stochastic printing is just a way of rearranging the dots in more random patterns so that more detail can be reproduced within the image. And you'd pretty much only want to use it with continuous tone images, photographs, fine art reproductions, things like that. If you have an inkjet or a laser printer, you're probably already aware of printer drivers. They need to be updated from time to time as technology changes. But drivers are software that control the communication between the printer and your computer. Generally, they're going to control specifically how the RGB, the additive color space, is converted to the CMY space. So remember, in the previous session, we were talking about managing that color process all the way through, where your computer is RGB and your printer is CMY. And so a driver is the, shall we say, the interpreter of the two color spaces. So when you go to print and you open up a print dialog box, you might get something like this. It's going to designate what printer you'll use. You'll have actual print settings that you'll look at, the size of the paper. You want Photoshop to manage your colors because that's where your color control is. You don't want printer managing the colors. But all the print settings and how the driver is going to interpret what's in the computer and what's in the printer and make them work together, it's all based on the settings that you input into the print dialog box. A gamut warning is when the image that you're printing has colors in it that cannot be mapped to the printed output. So usually you check that box in order to be alerted if things are going to be way out of gamut. When given the choice, you should always have the software manage the colors because, again, that's where your color control starts between your computer and the printer. So a rendering intent determines how color is reproduced. It's how color is matched from one color space to another. And it's perceptual, colorimetric, or saturation. And these use ICC profiles. We talked about the ICC in the previous session. A perceptual match will match color based on the human color gamut. So it tries to emulate our natural vision. And that means that working space colors, the colors, say you're working in straight RGB in Photoshop, which is a larger space than Adobe RGB, which might be what the printer would use. The colors that aren't in Adobe RGB will be scaled to fit within Adobe RGB. So there's an adjustment. You'll use perceptual match when you're creating G-clay prints, any sort of inkjet print, and you're printing any sort of continuous tone image for hard proofing or for any sort of higher quality desktop printing. You'll lose a little bit of saturation in the color. You'll lose a little bit of value contrast, but you'll have a really nice result. There are two types of colorimetric. One is absolute and one is relative, and whether it's one or the other depends upon what you decide to do about the white point. In absolute colorimetric, the colors will be mapped from one color space to another with as much accuracy as possible. And any out-of-gamut colors within the working space will be shifted so that they match in-gamut colors in the output space. So you're going to lose some color range. What absolute colorimetric does is it simulates the paper's luminance by adjusting the white point. So it will take into consideration what your substrate is. If you're printing with archival inks, you're creating high-end hard contract proofs, any sort of finely detailed hard proofing to show to a client, you'll use absolute colorimetric. With relative colorimetric, the white point will shift. It still maps colors as accurately as possible. It'll adjust your out-of-gamut colors in the working space to the in-gamut colors in the output space. And it maintains the original white point of your source image. This is what you use if you want to simulate the look of process color printing. Saturation match is for spot color simulation, where full range of value contrast, full range of saturation contrast aren't as necessary as they are in a continuous tone image. In a saturation match, the colors with greater chroma will be pulled to the extremes of the output gamut. So the vibrancy of the image is maintained, but you'll lose value contrast. This is good for simulating spot printing and with vector graphics and infographics, anytime where flat color is involved and you're not worried about gradations, value contrast, and things like that. So those are your 4 rendering intents. Black point compensation is a feature in Photoshop and Lightroom, and turn it on when you're converting to a CMY color space for printing. So this would not be used when you are printing off your inkjet. If you're printing G-clay prints in your home studio, don't use black point compensation. If the file has to be converted to CMYK from the RGB color space in order to be printed by the device, then black point compensation has to be turned on. Instead of the white point, it deals with the black point or the darkest part of the working space and maps that with as much accuracy as possible to the output space. It'll lighten the image overall, it'll desaturate some of the colors, and you'll lose some detailing in shadows, so your shadows will be flatter. So you have your shadows, your midtones, and your highlights. Your midtone and your shadow areas will lose some detail. You may have heard of swap. It is one of the color spaces. It's an output color space. It's not used much anymore because of digital printing. It's way too small to use. Instead, use what's called International Standards Organization, or ISO. ISO you may be familiar with digital camera settings and printer paper. It uses the CIE color values. It deals with types of paper. It deals with digital cameras. It deals with ink qualities and densities. So when you are printing not sheet fed but web, which is where you have the large rolls of paper, so you've got newspapers and other like tabloid publications will use web offset printing, use the ISO color space and the ISO settings. And that's basically it. Didn't go into great detail between all of these smaller issues, but they are things you should be aware of and basically know what things are, and therefore you have information to work with One of the things you should do if you print to a desktop printer is to print out the same image, say out of Photoshop or Lightroom, under each of the 4 different rendering intents. Then compare the differences in the prints. Use a glossy paper, use the same image, just print it out 4 times, each with a different rendering intent, and also with the black point compensation on and then off, and see what the visual result is. And you will basically self-educate based on your own printer. I can't advise you what the best thing to do is for your desktop setup. So this is something that you should manage yourself, and this is a way you can manage it. This is a way you can start taking control of your color process and your color output. If you have any questions, be sure to ask.